On the Earth, hydrogen only exists as a diatomic molecule called dihydrogen or in a combined form. This most abundant element accounts for approximately 70% of the mass of the universe. In its combined form, besides water, hydrogen occurs in plant and animal tissues as carbohydrates and many other compounds like hydrocarbons. It is, therefore, the third most abundant element on Earth, constituting 15.4% of its crust and the oceans. Hydrogen with atomic number 1 has 3 isotopes: protium, deuterium, and tritium. It is the only element whose isotopes are named. Protium has no neutrons. Deuterium has 1 neutron, while tritium has 2. Among the 3, protium, with a concentration of 99.98%, is the most abundant. The concentration of deuterium is only 0.0156%, mostly in the form of hydrogen-deuterium molecules. The concentration of tritium is about 1 atom per 10 raised to the power 18 atoms of protium. It is the only hydrogen isotope that is radioactive and emits low-energy beta particles. Because of its atomic number 1, hydrogen is the first element in the periodic table. However, its position in the periodic table is debated because of its resemblance to both alkali metals and halogens, as well as because of its unique behavior. Let us see how hydrogen is similar to alkali metals, yet different from the group at the same time. Its electronic configuration is 1s1. Therefore, like the alkali metals, lithium, sodium, and potassium, hydrogen also has only 1 electron in its outermost shell. Due to this, these elements possess similar electropositive character, allowing them to readily lose an electron to form positive ions. Thus, similar to alkali metals, hydrogen also shows an oxidation state of +1. For example, in hydrochloric acid, hydrogen has an oxidation state of +1, which is similar to that of alkali metals such as sodium and potassium, in sodium chloride and potassium chloride respectively. Like alkali metals, hydrogen acts as a strong reducing agent. For example, it reduces iron 3 oxide to iron, which is similar to the behavior of the alkali metal potassium in its reaction with boron oxide, wherein it reduces boron oxide to boron. Though hydrogen is similar to alkali metals in several aspects, it also exhibits certain properties that are different from alkali metals. For example, the ionization energy of hydrogen is very high as compared to alkali metals. It shows non-metallic behavior, unlike alkali metals. It exists as a diatomic molecule in the form of a gas, whereas alkali metals are solid and exist as monoatomic molecules. Hydrogen mostly forms covalent bonds, whereas alkali metals form ionic bonds. For example, HCl is covalent, whereas NaCl is ionic. Let us now see how hydrogen is similar to halogens, and yet different from the group at the same time. Like halogens, hydrogen has only one electron less than the nearest noble gas configuration. For example, it needs one electron to attain the noble gas configuration of helium. This is similar to halogens, which have an outermost shell configuration of Ns2, Np5 and need just one electron to attain noble gas configuration. The ionization enthalpy of hydrogen, 1312 kilojoules per mole, is very close to that of halogens like chlorine, 1255 kilojoules per mole. The oxidization state of hydrogen, -1, is similar to halogens in some of its compounds. For example, in sodium hydride, hydrogen has an oxidation state of -1, which is the same as that of chlorine in sodium chloride. The molecules of hydrogen and halogens are diatomic. Like halogens, hydrogen is non-metallic in nature and usually exists in gaseous form. In spite of several similarities with halogens, hydrogen also exhibits behavior that makes it different from the halogens. For example, unlike halogens, hydrogen has less tendency to take up an electron to form a hydride ion, whereas halogens form halide ions very easily. In a hydrogen molecule, atoms do not possess any unshared electron pairs, whereas in halogen molecules, every atom has 3 pairs of unshared electrons. The oxides of halogens, such as chlorine oxide, are acidic in nature, whereas hydrogen oxide or H2O is neutral. Because of this unique behavior of hydrogen, it is placed separately in the periodic table. This uniqueness of hydrogen makes it an industrially important element. Now, let's look at the ways to prepare dihydrogen both in the laboratory and industrially. In the laboratory, the most common way of preparing hydrogen is by the reaction of granulated zinc with dilute hydrochloric acid. The setup consists of granulated zinc in a conical flask fitted with a thistle funnel. In this flask, dilute hydrochloric acid is poured drop by drop through the thistle funnel. As dilute hydrochloric acid reacts with the zinc granules, hydrogen gas is released. The gas is collected by the downward displacement of water. Sometimes, the reaction stops midway as the bubbles of hydrogen gas stick to the surface of the zinc granules, preventing its further reaction with the acid. To avoid this, a few crystals of copper sulfate are added to the reaction mixture. Another common method of preparing hydrogen in the laboratory is by the action of metals like zinc and aluminium on strong alkalis like sodium hydroxide and potassium hydroxide. For example, zinc reacts with sodium hydroxide to give sodium zincate and hydrogen. Commercially, hydrogen is prepared by the electrolysis of water using platinum electrodes. Sulfuric acid is used to acidify water, making it a better conductor of electricity. When an electric current is passed through the water, it decomposes into hydrogen and oxygen. Hydrogen gas is liberated at the cathode and oxygen at the anode. The volume of hydrogen formed is double that of oxygen. Another industrial method of dihydrogen preparation is by passing steam over hydrocarbons or red-hot coke at high temperature in the presence of a catalyst, like nickel. The product contains carbon monoxide along with hydrogen. The number of moles of hydrogen and carbon monoxide produced depends on the hydrocarbon. For example, 1 mole of methane produces 1 mole of carbon monoxide and 3 moles of hydrogen. The mixture of hydrogen and carbon monoxide is called water gas. Water gas is further used for the synthesis of methanol and a number of other hydrocarbons, as it produces a lot of heat when burnt. Hence, water gas is also called synthesis gas or syngas. Syngas is also produced from sewage, sawdust, scrap wood, waste paper, etc. When syngas is obtained by the reaction of steam on coal, the process is known as coal gasification. It is difficult to separate dihydrogen from syngas. Therefore, the production of dihydrogen is increased by reacting the syngas with steam in the presence of iron chromate as a catalyst. The reaction produces mixture of carbon dioxide and dihydrogen. The carbon dioxide produced is removed from the mixture by scrubbing with sodium arsenite solution. This reaction is known as water gas shift reaction. Currently, almost 77% of hydrogen required by the industry is obtained from petrochemicals, 18% from coal, 4% from the electrolysis of aqueous solution, and 1% from other sources. Let us first discuss the physical properties of dihydrogen. Dihydrogen is a colorless, odorless, and tasteless gas. It is a non-poisonous gas with a vapor density of 1. Due to this, it is lighter than the air as its vapor density is 14.4. The solubility of hydrogen in water is very low. Under standard conditions, only 2 parts of dihydrogen dissolve in 100 parts of water by volume. Let us now look at the chemical properties of dihydrogen. Dihydrogen gas is chemically inert at room temperature. The chemical behavior of a diatomic molecule is determined by its bond dissociation enthalpy to a large extent. Bond dissociation enthalpy is the energy required to break a chemical bond. It is defined as the amount of energy required to break 1 mole of bonds of a gaseous molecule into fragments in gaseous state at 298 Kelvin and a pressure of 100 kilopascal. In a dihydrogen molecule, the HH bond dissociation enthalpy is very high. This because, as the size of the hydrogen atom is very small, it forms a very strong covalent bond. Thus, it requires an extremely high temperature to dissociate dihydrogen into its hydrogen atoms. For example, at 2000 Kelvin, only 0.081% of dihydrogen dissociates into hydrogen atoms. Only at a high temperature of 5000 Kelvin, we get almost 95.5% dissociation of dihydrogen molecules into its atoms. It is important to note that although a dihydrogen molecule is inert at room temperature, hydrogen atoms are very reactive. This is because they have only one electron in the 1s orbital, and thus they readily combine with almost all the elements to obtain a stable electronic configuration similar to that of helium. A hydrogen atom reacts either by losing one electron to form H-positive ions, or by gaining one electron to form H-negative ions, or by sharing electrons to form single covalent bonds. Let us now look at the reactions of dihydrogen. Dihydrogen gas at high temperatures reacts with highly electropositive metals such as potassium, sodium, and calcium. It combines to form their respective hydrides. In these hydrides, hydrogen exhibits an oxidation state of -1. For example, dihydrogen reacts with sodium to form sodium hydride. Similarly, hydrogen reacts with calcium to form calcium hydride. Dihydrogen burns an oxygen at high temperature in the presence of platinum as a catalyst, forming water and releasing lots of energy. Dihydrogen combines with halogens to form hydrogen halides. For example, it combines with chlorine in the presence of sunlight to form hydrogen chloride. When hydrogen is passed through boiling sulfur, it produces hydrogen sulfide. Dihydrogen reacts with nitrogen at 673 Kelvin and 200 atmospheric pressure in the presence of iron as a catalyst to form ammonia. Dihydrogen reduces metallic oxides of metals that are less reactive, such as copper oxide, lead oxide, and iron 3 oxide, into their respective metals. How does the reaction take place? The metal oxides are strongly heated in a combustion tube. When hydrogen is passed through the tube, the metallic oxides get reduced into their respective metals. Dihydrogen reacts with vegetable oils in the presence of finely divided nickel as a catalyst to give hydrogenated products such as edible fats. Because of its unique properties, like forming non-polluting products and burning in air, dihydrogen gas has many commercial uses. It is used as the rocket fuel because of its high calorific value. An oxyhydrogen blowtorch that is used for cutting and welding purposes uses dihydrogen and pure oxygen. The reaction produces temperature of up to 4000 Kelvin. Dihydrogen is also used in the synthesis of ammonia by Haber's process to manufacture nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati. Here, vegetable oils such as soybean are hydrogenated to obtain vanaspati. Commercially, it is used in the preparation of hydrogen chloride as a reducing agent to reduce metal oxides into their respective metals, and also in the manufacture of metal hydrides.